Okay, hello and welcome to lesson 5.1, where we're getting to start unit 5. And the premise of this unit is we are now solving quadratics. So all of unit 4 we spent writing. We talked about factored form, vertex form, standard form, and reading word problems and writing the equations that model those word problems. But now we finally get to solve. We finally get to solve these quadratics, and we're going to look at a variety of methods of doing so. On this first lesson, day 1, we're going to be looking at solving by factoring, mainly because we've been focusing on factoring as an important skill, and a lot of quadratics can be solved through factoring. Maybe not some of the real-world application ones, but a lot of perfect quadratics can, and that's really nice. So we're going to go through that on this one, and then day 2, we'll be doing simplifying radicals and introduce you to complex numbers, so you can really get to see all the solutions possible for quadratics. And then day 3, we're going to do completing the square and quadratic formula, so you get to see another new methods of what to do when you can't factor. So methods, because this isn't always going to work. Not all quadratics are factorable, but the ones that are, you can factor pretty easily, pretty quickly, without having to use a calculator most of the time, and that's pretty nice. So let's start. Okay. But before we get into factoring techniques, because that's what I'm going to show you in this, we're going to walk through what it means to solve by factoring, and then I'm going to show you a variety of new techniques that you may or may not have seen in Algebra 1. You may have not. I don't know. It kind of depends on your teacher and depending on how much they've pushed you in that setting, okay? So first things first, when solving any quadratic equation, and this goes for everything, not just factoring, but for solving any quadratic equation, we want to rewrite the equation in standard form and set it equal to 0. So that looks like ax squared plus bx plus c equals 0. That's what we want to do. You will then factor the standard form equation and identify its roots. Because remember, what do we mean by the word solutions? Solutions means roots. It means what makes y equal to 0. It also means zeros, right? Roots, solutions, zeros. And sometimes we can think of these as x-intercepts, although they're not always x-intercepts, okay? Okay, now this is all going to use something called the zero product property, which is just a fancy name for a rule you've known and been using since grade school. 0 times any number n equals 0. This is what the zero product property says. If I have any number times 0, the result is 0. This is very useful for factored form because when you have a list of stuff, factored, if any one of these factors equals 0, then that helps you solve for the roots, right? Because if you set it equal to 0, then you just need to analyze the factors, and when those are equal to 0, and then that's going to give you the solutions to the quadratic. So let's see this in action, okay? Example 1, I've got x squared minus 4x, or x squared equals 4x plus 21. I need this in standard form, so I'm going to rewrite it as x squared minus 4x minus 21 equals 0. I am put in standard form, which is ax squared plus bx plus c equals 0. Okay? I'm only going to write that once. Now factor. So I'm going to factor this using my little factoring puzzle, negative 21 and negative 4. And I see that negative 7 times 3 gets negative 21 and adds to get negative 4. Now, because a equals 1, so I'm going to say since a equals 1, I don't have to factor by grouping. I don't have to do that. I can just use a shortcut, and say that this factors as x minus 7 times x plus 3, which equals 0. Awesome. Now see, here's what the zero product property says. If x minus 7 equals 0, then that satisfies this equation, right? If x minus 7 equals 0, then 0 times x plus 3 equals 0 is true. Thus, x equals 7 is a solution. Do you see it, right? X minus 7 equals 0. So if I add 7 to the other side, x equals 7 is a solution. And this makes sense because factored form says x minus root 1 times x minus root 2 with a stretch factor a equals 0. Well, r is the root, right? And in this case, it's minus 7. This other one's plus 3, so that's like minus negative 3. So I can already identify the roots if I knew factored form. But this is the more official way to describe it using the zero product property. And I can do something similar here. This fella, if x plus 3 equals 0, then x minus 7 times 0 equals 0 is true. Thus, x equals negative 3 is a solution. So I'm going to say, therefore, x equals, the solution set is positive 7 and negative 3. Okay. And done. Okay? All right, let's move on. Example 2. I really only needed to do this first example, but I wanted to give you a plethora of examples to refer to just in case you get stuck. Okay? So example 2, I'm going to put this in standard form again. I'm going to say 6x squared. I'm going to add 7x to the other side, and then subtract 3 to the other side, and this equals 0. Now, a does not equal 1, right? So a not equal 1. So use grouping. That's what we're going to do. So we're going to do little cross puzzle. 6 times 3 is negative 18. 7 down below. And I think 9 and 2, where 2 is negative, multiplies to get negative 18, adds to get 7. So if I use grouping, I get 6x squared plus 9x minus 2x minus 3 equals 0. This then factors as 3x times 2x plus 3 minus 1 times 2x plus 3 equals 0, which now factors as 3x minus 1 and 2x plus 3 equal to 0. So now that it's in factored form, right, I say 3x minus 1, 2x plus 3 equals 0. We're going to do two things. If 3x minus 1 equals 0, then 0 times 2x plus 3 equals 0. Check, right? Thus, I have 3x minus 1 equals 0 implies if I add 1 to the other side, I get 3x equals 1, and this implies x equals 1/3. Then in green, I can say here, same idea, if 2x plus 3 equals 0, then again, 3x minus 1 times 0 equals 0 is true. So say thus 2x plus 3 equals 0 implies that 2x equals negative 3 by subtracting 3 to the other side, which implies x equals -3/2 by dividing by 2. Therefore, x equals -3/2 and +1/3. And those are my solutions. So I illustrate this example because in example 1, it's very easy to visually identify the roots as 7 and -3, making that equal to 0. Now, if you're really good at fractions and mental math, you might be saying, Mr. Spake, example 2 is easy too. But I personally think it's just a little bit more challenging because you have to be careful with adding all that stuff in your head, right? 3, I'm going to circle this, 3 times 1/3 equals 1, and then 1 minus 1 is 0, which makes this whole thing true. Okay, so that's why x equals 1/3. Same idea for -3/2. So you're setting the factored term equal to 0 and solving for x. That's very important. Usually it will be, it's important to understand this idea now because we will get into more complicated factors. And so our factors are going to start being much more complicated with higher order polynomials. So we really want to understand this idea of zero product property now so that it's smoother sailing later on. All right, now last example here, example 3. This is just a quick one using GCF because I wanted to throw this in here to remind you that's always what you should be looking for first is greatest common factor. Don't try and factor this using the cross puzzle. Just notice that they both have 5x in common and that this is now x minus 9, which equals 0. So we have two things. Here, if x equals 0, then 5 times 0 times x minus 9 equals 0 is true. So x equals 0. And then the same idea for x minus 9. If x minus 9 equals 0, then 5x times 0 equals 0 is true. So x equals 9. Therefore, x equals 0 and 9. Done. Now, what I'm writing here in the blue and green every time, I don't actually expect you to write a full sentence like that. I'm writing that so you can really see it visually and have it in your notes for reference, okay? You can just jump to these. I mean, honestly, if your work shows this and then factored form, and then you give me the answer, that's fine, okay? You show me standard form, you show me factored form, you show me the answer, I can follow that, okay? I don't need a ton of work. I'm not saying, oh, you have to write out these sentences. Oh, you have to write out these sentences. But they might help you understand the idea if you're struggling with this. Okay, let's move on to factoring techniques. So now we get to talk about new factoring techniques that maybe we've seen, maybe we haven't seen before. So, quick reminder, we have seen the first 4. So we've seen greatest common factoring, that was in lesson 4.2. We've seen the case of factoring when a equals 1, that was actually example 1. We've seen factor by grouping, which was example 2. And we've seen the difference of squares identity as well, because I introduced that very briefly. I do want to go over difference of squares one more time, because I think it'd be good to see again. And then we're going to focus on 3 new techniques: perfect square trinomials, guess and check, and the kickback method. Now, all of these, so if you understand all of these factoring techniques, you don't have to watch the rest of the video. But they're useful techniques that will help you build speed and fluency, okay? because, and I make you practice factor by grouping a bunch first, because it's the nice, methodical, precise way to factor. But these methods are often much faster, much more useful, save you time. And so that's why we want to look at these methods for shortcuts and innovative thinking. They're not just things to memorize. They're tools to use to solve difficult problems. Okay, so let's look at difference of squares. Now, the difference of squares identity, I don't know if you recall, says that a squared minus b squared factors as a plus b times a minus b. And you can see this if you distribute this stuff. A times a is a squared, a times negative b is minus ab, b times a is plus ab, and b times negative b is negative b squared. But these cancel, and so it's a squared minus b squared. Okay? I'm just going to erase that because I don't need it. All right. So notice here, 4q squared minus 9. Well, 4 is a perfect square, as is 9. And I can rewrite this as 2q quantity squared minus 3 squared. So in this case, 2q is a and 3 is b. So this implies that it factors as 2q plus 3 times 2q minus 3, using the difference of squares identity that's listed in yellow. So, know your perfect squares. Exclamation point, exclamation point, exclamation point. You got to know these, all right? If you don't know your perfect squares, if you don't know that 16 is 4 squared, you will not be able to do this successfully. You must know your perfect squares to be able to recognize this, okay? All right, let's move on. Now, let's talk about perfect square trinomial. Now, this is new. At least it's new for if you've never seen it prior to my class, okay? So a perfect square trinomial is if I take a plus b and I square that, then that is a plus b times a plus b. And that is a squared plus ab plus ab again plus b squared, which means this equals a squared plus 2ab plus b squared. This is the pattern you look for. The giveaway is those first and last terms, a squared and b squared. If you identify those as perfect squares, chances are you might be able to factor this using thinking of it as a perfect square trinomial. And real quick, the vocabulary of this perfect square trinomial. Trinomial means 3 terms. Those indicate it's a trinomial because there's 3 terms, a squared, 2ab, b squared. So that's a trinomial, and it factors as a perfect square, something squared. So that's why it's called a perfect square trinomial. So now looking at this, looking at 25x squared plus 10x plus 1, I want you to notice 1 squared is 1, and 5 squared is 25. So I could look at this as 5x quantity squared plus 10x plus 1 squared, like so. But of course, this is like saying 5x squared plus 2 times 5x times 1 plus 1 squared. And this is a perfect square trinomial. I don't like how I wrote that. I'm going to rewrite it again. Perfect square. Oh, I hate that too. I'm sorry. I waste so much time in my videos. Just real-time editing. Perfect square trinomial. Trinomial. Okay, now it looks good. Now it looks good. So then, A equals 5x, B equals 1. So this factors as 5x plus 1 squared. Done. Done. There's your perfect square trinomial. All right. Draw a nice line like so. Nice. So that's just my little divider there. So what I would do is pause the video and try number 6 here. That's what I would do. But I'm just going to go ahead and walk through it. If you're looking at 9x squared minus 12x plus 4, this could be reinterpreted as 3x quantity squared minus 2 times 3x times 2. Notice because 2 times 3 is 6, times 2 is 12, and then 4 is 2 squared. So this is going to factor. Notice this is a minus b squared is a squared minus 2ab plus b squared. You can get that by foiling that out if you want. So this follows pattern. So a equals 3x, b equals 2. So this factors as 3x minus 2 squared. Okay, nice. Those are perfect square trinomials. Now, I'm going to let you know, those can take a while to really get used to, notice, and see fluidly. All right, it's not something that just happens overnight for most people. It takes lots of practice, and it may even take months of seeing this. Who knows, maybe even years before you're really able to do it fluidly and cleanly. But for now, just practice on trying to recognize them, okay? And I'll be handing you problems like that to help recognize those. I want you to know you could solve either of these, example 5 or example 6, using factor by grouping. But if you were just able to notice this trinomial pattern, you would instantly factor it, instantly. All that stuff, all those intermediate steps, you can recognize that stuff mentally if you practice enough. So you don't even have to write it. You can go straight from just looking at it, boom, factored. And that's the perfect square trinomial. Okay, last two, and then I'm so glad to be done. Not because I don't enjoy talking about this, but because it's late and I want to go do other things right now, as I'm sure maybe you do. Okay, let's talk about the guess and check method. So here's a quick word about this. This method is most effective when the a value of the standard form equation is prime. This is going to get more difficult when it's not prime, particularly if you use a lot of composite values, like high composite values that have multiple factorizations. That can be too much, all right? It's highly reliant on mental math capabilities. Did I spell reliant right? You know what? I don't know. That looks funky to me. Reliant. Reliant. Did I spell that right? Okay, it looks like I did. I just want to be sure, you know? Okay. Heavily reliant on mental math capabilities. This means it can be more prone to mistakes and makes checking your work a more difficult task. Okay, so this, I mean, it's mostly mental mistakes because of positive and negatives. You got to be really careful with your positive and negatives when working with the guess and check method. But if you can get good at it, it's going to save you a lot of time. That whole factoring by grouping business, this will be instant. It'll be instant. But I do recommend, if A is not prime, I don't use this, okay? It's just, you might just end up wasting more time. And factoring by grouping, or what's about to follow is the kickback method. Either of those might be more effective. Okay, so let's do this. So the way I'm going to reason this is when I look at 7x squared, I know that it has to factor like one of these, right? It has to factor in two ways since it's a quadratic. It's something times something. Now, to get 7x squared, only 7 and 1 multiply to get 7. So using the fact that it's prime, I know that 7x times x gets me 7x squared. This is highly useful because I've already got half of it down. And now I just need to find two numbers that multiply to get -6. Now, you have a few options here because you can try 6 and 1, or you can try 2 and 3, I believe. So let's go with, 2 and 3. Okay? Because here's what we're doing. We're trying to find two things that multiply to get -6. By the way, the higher the C value is, the harder this gets too. So if C is prime, that's super useful as well. If C is not prime, this gets messy. So what are my choices? I'm going to say blank here, blank here. What are my choices? Well, I have 6 and 1, or I have 2 and 3, right? Because 6 times 1 gets me 6, and 2 times 3 gets me 6. So pick one, right? Look, let's pick 6 and 1. So if I do this, 7x, x, here's 6, here's 1. Or 7x, 1, x, and 6, right? So let's do some mental math here. 7 times 1 is 7x. 6 times 1 is 6x. Can 7x and 6x be used to obtain 11x? Because when I add these middle terms, these two terms, those should add up to that value, -11. No, this does not work. Now let's try 7 times 6, which is 42x, and 1 times x is 1x. Can this be used to obtain 11x? No. So I'm going to draw a streak through this. That doesn't work. So guessing and checking there, not working. Let's try the next set. Okay. 7x and 2, x and 3, and then 7x and 3, x and 2. So if I do 7x times 3, that's 21x, and 2 times x is 2x. Can this be used to obtain 11x? No, it can't. When I'm saying obtain 11x, I'm thinking if you add those, right? Add or subtract. Like 7 plus 6 is going to be 13. It's not going to be 11. And I don't even really care about signs that much right now. I'm just thinking about the quantities themselves. Now if I do 7 times 2, that's 14x. And 3 times x is 3x. Can I obtain 11x? Yes, I can. Because negative 14x plus 3x equals negative 11x. So, how do I get negative 14? By making this a minus, right? Because 7 times negative 2 is negative 14, and positive 3 times x. So, therefore, this factors as 7x plus 3 and x minus 2. And ta-da, we have done it. Okay? Whew. Yeah, that one was kind of tough. That was a lot. But, yeah. When you have like a 2x squared or a 3x squared or even a 5x squared, it's guess and check's usually going to be pretty good. I think we got a little unlucky here with the fact that 6 as a C term also has multiple factors, like 6 and 1 and 2 and 3. If the C value is prime 2, well, then you'd only have one pair of these to look at, and then if you only had that one pair to look at, it'd be very, very quick. And the more you practice this, the better your mental math gets. So that's the guess and check method. You're basically just looking at those beginning values, using them to get this, and then you're considering what the end value should be to get you the C value. And so you're placing those, because they can go in either spot, and then you kind of do the same thing here. And then you just do some mental math of forward manipulation to see if they'll add up to get the middle term. That's kind of how the gist of guess and check works. Okay, last one, the kickback method. And this one doesn't take nearly as much time to go through. Now, this is not a very official factoring method. I think you can find it online, but I don't think I've ever seen it in a textbook or any formal source because it's, well, I don't know. I guess it's kind of a cheat. It's not a bad thing. It's super effective in helping you solve quadratics. The only reason I don't like it that much is it's not very intuitive. It doesn't make a whole lot of sense as to why it works. I need to investigate more personally to see if there is a reason why it works, because I'm sure there has to be some explanation. Nobody could just figure this out without mathematical reasoning, but I don't know. This method also starts to fall apart for higher order polynomials, I think. I think it's only really good for quadratics, so that's one of the drawbacks. Whereas guess and check is still useful for other things, not just quadratics. So let's try this out. Here's how the kickback method works. The kickback method works by factoring like normal. 7 times negative 6 is negative 42. And down here is negative 11. Now, what times what adds to get negative 42 and adds to get 11? Well, you can test a bunch of things, but the result you're going to come up with is negative 14 and positive 3. I mean, you could have paused the video and tried to figure that out, but if you need a moment, just pause and think about it, okay? You will get those as factors. Now, the way the kickback method works is instead of doing factor by grouping, I would write 17x squared minus 14x plus 3x minus 6, and then I would group, right? The kickback method says kind of like the shortcut for a equals 1, write this as x minus 14 and x plus 3, except what you're going to do is take the 14, divide it by 7. Take the 3 and divide it by 7. And when you do this, if it's divisible, you get x minus 2, because 14 over 7 is 2, times x plus 3 sevenths. But that's not proper factored form, so you take the 7 and kick it back to the front. So this factors now, therefore, as x minus 2 times 7x plus 3. And that's the kickback method. And you might be saying, what the heck, Mr. Spake? You went through this guess and check method. You went through this perfect square trinomial stuff. You went through all of this nonsense by grouping. Why didn't you just show me this first? That's the easiest. I will tell you it's a student favorite. It's very effective. It's useful. We do love it. But be cautious, because it's not the end-all be-all. It's really not the best method for factoring in general. It's a sort of specific method for quadratics that's very useful. Okay? We'll see this again when we talk about higher order polynomials, but for now, these are our factoring methods. I hope you've enjoyed watching them, and there you go. You can now solve quadratics by factoring, and that pretty much covers all our bases. All right. Have a great rest of your day or night or morning or whenever you're watching this, and go take a break. This is a bit of a long video. Go drink something. I think I said that in one of my other videos, but just go take a break, all right? Take a mental break. Go yawn. Take a nap. I don't know. All right. I'll see you later.